We now look at an example of bar delta filtering to get an idea of how well it works. And in the process of the example, we also introduce a new idea of how to validate the operation of algorithms inside of your battery management system. There's two basic approaches to algorithm validation, and one of them is called hardware in the loop, where you actually have real data, real cells, everything just operating essentially. And this is going to use your final production code. It's just going to be the real deal. So it's going to tell you a lot of things. It's going to tell you if everything runs. There's no fooling anybody with hardware in the loop validation. But the issue is that sometimes it's hard or impossible to determine the truth against which you need to compare your estimates. How do you know what the true state of charge is for a real battery cell? How do you, and that, you could maybe calibrate a test very carefully with perfectly pre-charged cells, and you could maybe perfectly discharge them at the end of the test and get some idea of the initial and ending states of charge or something like that. So you could do something like that. But how would you know the internal states of the cells, like in an ESC model, what the diffusion currents are and the hysteresis states and so forth? So hardware in the loop has to be done absolutely before you build your final product and you sell it, but it's not the first step. Instead, what you would tend to do is you'd probably do some simulations in MATLAB, but you would also do what I'm going to call desktop validation. And instead of using real test data, we make some synthetic test data, some simulated test data using a model of a cell. So you might have an actual recorded profile of current versus time that you expect your application to see. You run that current versus time through your cell model, your ESC model or whatever, and you create synthetic test data that has true states and true outputs and everything. So I know all of the cell states, and also when I'm doing the validation, I also have the algorithm states, so I can compare one-to-one to see how things are working. This is super useful for tuning algorithms. The covariance matrices required in an EKF or SPKF are not really well known in any kind of theoretic sense, so we would manually adjust them until we get performance that works well over the entire expected operational range of the battery pack. And so doing this on a desktop is much cheaper and faster and easier than doing it in real hardware. And then of course you test it in hardware later. A downside is that the validity of your results is limited by the accuracy of your cell model, because you're creating this synthetic test data against which you're comparing everything, and if your data is wrong, everything else is going to be suspect also. So make sure your cell model is pretty good. With desktop validation, here's the picture, is we need a data generation component, and that's what I've drawn in this box here. This creates your synthetic data based on drive cycles of current versus time or power versus time and different initialization parameters. You could have things in there like the temperature versus time. You could have simulations of cells having different ages, new cells, old cells, a mixture of new cells and old cells. You could put in there, because you're generating not only the truth data but also the synthetic measured data, they don't have to be the same. So you could introduce measurement noises of various sizes and measurement biases and sensor faults inside of your data generator system to see how your algorithms respond. And not only can you, you should do that as well, because it's much easier to generate a synthetic sensor fault than it is a true sensor fault in a hardware in the loop scenario. So you can really do a wide range, a large suite of simulations using this methodology to really exercise your algorithms well. So we need the data generation. We also need some kind of a BMS algorithm simulation component. And I think it's beneficial to do this in two different ways. One of them is on the PC, maybe in MATLAB first. You run this data through your algorithms and you get results, and you compare the results to the known truth from your data generation system. So this here is truth plus the measured data. Here I'm using only the measured data part. I don't use the truth. That would be cheating for computing state estimates. But in the evaluation, I'm comparing the measured or the estimated and the truth to see how well I did. And that gives me my first indication of, do the algorithms work or not. If they don't work in that scenario, they ain't going to work in practice because real life throws things at you that you weren't expecting. So that's step number one. Do it in MATLAB or your prototyping language. Step two is recognize that your battery management system is probably not going to run MATLAB. Certainly not. It's going to run probably C. Maybe some other language, but probably C. So on the PC, again, you write your algorithms in C, and you put some kind of wrapper code around them that loads, instead of reading sensors, it loads the data from a file and pretends it's reading from sensors and runs your algorithms. You should get identical, exactly the same results out of your C code. If you don't, that means there's an error, most likely, or maybe your C code is single precision floats and your algorithms in MATLAB are double precision floats. You would expect some very, very small differences because of that. And if you get large differences, either your algorithm is very sensitive to precision or you made an error. And that allows you to track down a C code error on the desktop, which is a very nice development environment. Once you've convinced yourself your MATLAB and C code are giving you the same results and both are acceptable, you move your C code into the actual battery management system. And once again, it's convenient on your battery management system to have some kind of a software switch that instead of reading physical sensors, you can read from some data log, so you can still use these measurements here on your battery management system software to run through all the algorithms and produce results, and again compare and evaluate the true and the estimate results there. And all three of these should give you exactly the same. PC-based MATLAB, PC-based C, and BMS-based C should give you exactly the same results because you're using exactly the same data and notionally the same algorithms. That is a good approach, I believe, to stepwise implementing BMS algorithms. You certainly don't implement it first in C on a BMS hardware and hope that it works. If you do, good luck. You have to be the world's greatest programmer and then some for that to make sense. And maybe you are. Any way we do this, the scenarios that we choose to validate over should include normal operation, things like improper state of charge initialization because maybe my first voltage reading was wrong because my voltage sensor, there was a timing fault or something. Some kind of sensor failures with sensor faults and sensor noise, some kind of a temperature drift to see if this works well over different temperatures, mixing new cells and old cells, using different drive cycles, so you don't convince yourself using UDDS that this thing works perfectly and then try it on something else and find it doesn't, and current sensor bias. You can make hundreds of different simulation scenarios to cover all of these different possibilities, and yes, it will take some time to run those on a desktop, but it would take an awful lot longer to run them in real life. So this is a pretty good way of validating algorithms. We did this with the bar delta approach to get an idea of, does it work, and is it in fact faster? Does it give us the kind of speed up we were hoping to achieve? So in this case, we simulated a 4-cell battery pack, a very small one. It's a proof of concept with the input current corresponding to a UDDS cycle evaluated on a small vehicle. So one cycle, then a rest period, then another UDDS cycle and a rest period. So it's a fairly short test just to see how the bar delta method responds to that. Because I'm simulating, I'm doing synthetic data, I can very easily simulate cells having different capacities. So in this case, 6.5, 7, 7.5, 8 amp hours for the 4 different cells, different resistances for the 4 different cells, and different states of charge for the 4 different cells. And it's very easy also to include a true current sensor bias to see if we can estimate that with any fidelity. That was the truth. The algorithms, on the other hand, were initialized a little bit away from the truth. So we said, suppose we assume all cells have 6.2 amp hour capacity, which is quite different from the true capacities. 2.25 milliohms resistance, which is somewhere in that range, but certainly not true for all the cells. An estimated current sensor bias of 0 amps, which is not true. And we initialized the SOC estimates based on the initial voltages. So those are pretty close, in this case, to the true SOCs of the cells. For the pack average bar filter, I used sigma point Kalman filter. And for the delta state of charge, resistance, and capacity states, I used EKF filters. The SOC delta filter, I also used SPKF, but the resistance and capacity, I used EKF. And now we get to look at some results. This is the input current to this particular synthesized battery pack. And these are the 4 different recorded battery pack cell voltages. And you can see that they are separated because the initial states of charge are separated. That's the main reason for the vertical difference, but there's some difference in the dynamic nature also because the cells having different resistances and so forth cause them to be, some of them to have more variability than the others. So that's the data used. Now some results. The top left plot shows the total state of charge estimate for all of the cells. For the 4 different cells, and the blue line is the true state of charge and the green line is the estimated state of charge. And we see that the state of charge estimates are pretty good. And in fact, as the filter learns things like resistance and current sensor bias over time, the state of charge estimates, I would argue, are improving. So there's some variability here that we don't see there. For example. So using the pack average plus the 4 SOC state filters, delta state filters, we get good estimates of state of charge. The top right picture shows resistance estimates, and again, remember we started all resistance estimates at one common point. And for a little while, the resistance estimates are hunting around, but over time, over these 2 drive cycles, by the end, I am very close to the actual resistances of the cells. And of course, if we store the data after this drive cycle and start not at 2.25 milliohms next time, but start with these values, it will continue to improve. And we will get consistently good resistance estimates over the life cycle of the battery pack. Those are the absolute quantities. We can also look at errors, estimation errors. That sometimes is more telling. And in this case, I put the filter error bounds on the plot also. It was a little too messy to put them in the other ones, but here I put the error bounds on so you could get an idea. And we see this is the pack average state of charge with error bounds, and it stays within. And in this simulation example, the pack average state of charge is always within 1% of truth. And that's pretty good. And then the delta SOC, so the total bar delta SOC estimation errors for all cells, are plotted in this plot. And I think you can see that for this period of time the errors are a little worse than for this period of time, so there is learning happening from one cycle to another and improvement. The error bounds are maybe larger than we would expect. Certainly the truth is well within the error bounds, but all I did was I took sigma pack, well, the sigma of the pack average filter plus the delta sigma for the bar delta filter and added them together in order to get these bounds. That may not actually be exactly the right thing to do, but that's what I did do here. And it seems to be conservative, which is good for error bounds to be. Some other quantities, we have the pack average resistance, and notice that within very little time the pack average resistance filter converges to the truth, and the error bounds are still shrinking slowly over time. And also notice that the current sensor bias, this is one of the harder things to estimate, started out at 0 when the truth was a half, and sure enough the filter is learning what the current sensor bias is, and by the end of the simulation it's really quite close. And that's one of the reasons why the results that we saw earlier on the page improve from cycle to cycle, is that we're able to estimate that current sensor bias with pretty good accuracy. And I don't show results here for capacity because capacity estimates, while they evolve in a similar way to the resistance estimates, the time scale of the adaptation is much longer. We'll see why next chapter. Basically, it's because there's very, very, very little information in the voltage about what the cell capacity is at any point in time. We have to aggregate over a long length of time to get much information about cell capacities. However, we do adapt the capacity, and it does go in the right direction, and it does give us fairly decent estimates of capacity as well. It does not allow us to change, to attract abrupt changes in capacity, such as if I had a complete failure. We'd have to find some other way of doing that, but normal capacity fade can be tracked fast enough because normal aging happens over years and decades and not over seconds. And finally, if the results are accurate enough, and I argue that they are for most applications, did we achieve our primary goal of speeding up the algorithm with bar delta filtering? And these set of examples were originally run quite some time ago, as you might gather from the processor that they were run on. So please don't take the absolute numbers in milliseconds as being representative of what you could do on a modern processor. Instead, take the relative numbers as an indication of the improvement of one method over the other. So the baseline performance was, in this case, this was not 4 cells. I repeated this for 100 cells. Yes, I did. So a pack comprising 100 cells. And the CPU time per iteration was 5.272 milliseconds to update all 100 cells one iteration. So that's the baseline. That's the kind of the simple-minded approach of generalizing the sigma point method to a 100-cell battery pack. If instead of doing that, we used one bar filter only, a pack average filter with no delta filters at all, it took 0.067 milliseconds per iteration, which is not quite a 100-to-1 speed up, because in this case I'm also estimating current sensor bias and the pack average resistance and the pack average inverse capacity. So I'm estimating more with this filter than any of these. So the speed up isn't quite 100, but it's still pretty good. It's almost 80. The worst case speed up would be if I updated every iteration the pack average filter, and at the same time we updated all 100 delta filters every iteration. 0.19 milliseconds, speed up of almost 30. And if I did the pack average filter and half of the delta filters every iteration, and so every iteration I would do half, then the other half, then half, then the other half, and so forth, and that was a speed up of 43. I didn't try other cases, could have, but didn't. In this particular case, my target goal was a speed up of 40, and we were able to achieve that quite handily and still get really good accuracies. This was hand-coded C code, so all of the operations were optimized as much as possible in every case. Now, that relies on my ability to write C code, which is, I think, okay, but maybe not world-class. So someone else could have done this and had somewhat different numbers, but I think this at least indicates that the bar delta method, 1, gives us good accuracies, and 2, with good speed up. And so there's, in the extreme limit, there's almost no penalty for estimating all cell states of charge versus just a pack average state of charge. That brings us to the end of this chapter. It's been quite a long chapter, I think the longest one in the course. But we've introduced some important concepts that we're going to see again next chapter as well, with the Kalman filtering and so forth. In this chapter, we've seen both good ways and poor ways of estimating state of charge for all cells. I hope that I've been able to convince you that model-based methods are preferred and that Kalman filter-based methods are really good. They're optimal in some sense. The nonlinear methods are at least intelligent methods to use, if not optimal. These work well in practice. They've been established since the 60s. They have not really been superseded. There's somewhat different approaches out there, but there's not really anything that's definitively superseded the Kalman filter-based methods. They just really work. And I think, in my experience, they work really well for battery applications too. The Kalman filter estimates the entire state, not only state of charge, so we can use Kalman filter for degradation predictions. We've seen a little bit of that in this chapter. We're going to see more of that next chapter. Also, estimating the entire state has advantages when we're predicting power, and we'll see that in the future as well. So there's some really important side benefits for using Kalman filter versus a simple method, and I think that together, by the end of the course, you'll see that all of these pieces fit together really nicely for a very nice packaged battery management system. When it comes to understanding the Kalman filter, I've introduced in this chapter only the minimum of what I felt was required for you to be able to understand how it works. There's a lot of nuances that are really unexplored, and we have a whole course in Kalman filtering, and you can look up those course notes and lecture videos on my website if you are more interested in that. So there's a lot of depth and breadth and some tricks you can do, like square root filtering and things like that. If you're really excited about this and you want to try out a particle filter, you could look at how to do that from those course notes also. We don't have time in this course. I have time only to introduce this much and then move on to some other topics in battery management. The next step is to look at state of health estimation, and that turns out to be a form of parameter estimation, which is what we do in the next chapter. Before we get there, I do want to point out there are some appendices, and I'm not going to go through them here, but I'd like you to be aware of them. We have in this chapter introduced the general sequential probabilistic inference solution as the foundation on which Kalman filtering is built. And I've got a table here that is your reference for what the 6 steps are. How do we initialize, what do we define, and what are the 6 steps? And then we moved on to the linear Kalman filter, and again, what was the system model we assumed? How do we initialize it? And then what are the 6 steps derived from the sequential probabilistic inference but adapted to this particular linear model? And then from that we looked at the nonlinear extended Kalman filter. So what was the assumption of the model? What were the definitions that we used? How do we initialize? And what are the 6 steps of the EKF? And then here we have the sigma point Kalman filter also. The same kinds of ideas are there, and that kind of spreads itself over 2 pages. I put those there as reference. If you are going to be implementing any of these filters, I believe that this could be quite helpful to you, just to go to this and say, oh yeah, I got to implement this step and this step and this step, and hopefully the code that was in the main section of notes is also helpful. And finally, we talked about the chi-squared test if we are looking for voltage faults, and I mentioned that there was a table in the appendix that would help you to compute the critical bound, the critical value of the chi-squared test, and this is the table that does it. And so you would look up, in the case that we did, we had 24 degrees of freedom, and so we're looking at this line right here, and then in the one of the tails we had 97.5%, which gives us this 12.4. That was one of the numbers we saw. And in the other tail, we had 0.025, which gives us this 39.36 number that we saw earlier. So that's how you would use the table. Find the number of degrees of freedom, find the upper tail area that you're looking for, and that gives you the value to use in the NEES test. All right. Well, we've made it through Chapter 3, and this is great news. Time to move on to looking at state of health.